Good morning, class. Sorry I couldn't be there today, but that's how it goes sometimes. I'm going to take you through lesson 2.3a, and we're going to get a little work done today, even in my absence. So if you would, open your books or notebooks there to 2.3a, comparing linear functions. While you're opening those, it should be safe for me to assume that you have done section 2.2, contextualizing linear functions, that you did all of the even questions, and that you watched those videos to determine whether you got those questions right or not. If you still have questions about section 2.2, I will cover that when I'm back, hopefully tomorrow. So here we go. Let's section 2.3a. What I'm going to do here is I'm going to actually start by going through 2.3a and reading and highlighting with you. So if you would, get out your highlighters. If you don't have one, there's some on my desk there. You can borrow those, but as always, make sure you put those back when you're done with them. So I'm going to read and highlight with you, and then I'm going to go through a set of notes. You can see that at the top of the tabs here. So anyhow, in this section, we'll be using slope-intercept form. And I'm not going to highlight that, but I am going to underline that slope-intercept form. Just as a reminder, that is y equals mx plus b. So we're going to use slope-intercept form of linear function equations to be able to accurately compare functions. We may need to get the functions in the same representations, solve various representations of functions, find the rates of change of each representation, and find initial values of each representation. That all that means is, hey, we're going to be looking for rates of change and initial values, no matter how it's given to us, and we're going to compare those. So the first thing we want to do is we want to define the variables that are in the situation. Okay, this is very similar to what we did yesterday. We're still looking for the context. We want to make sure that we can correctly identify the initial value in each of the situations so that we can define our variables correctly. The key to equations is finding the lowest terms of the proportion, ratio, or of slope. In other words, if I had 14 over 7, if I found my rise to be 14 and my run to be 7, I need to be able to reduce that to 2. That's all that's saying there. So let's look at example 1. A company gained a value of, at the rate of $200,000 per, there's the kitty cat, per day after its IPO, initial public offering, of $1 million. So right away, we can say that $200,000 per day is our rate of change, and the $1 million is our initial value. So what's actually being compared here? The hint is the word rate, which compares the values in dollars and the number of days after a company's opening to its public stock. I know that doesn't mean anything to you, and you don't really care about that. But what we're looking for is what's the rate of change, what's the initial value, and then what's the total value of the company in dollars. So this V, is it going to be our independent variable or our dependent variable? Is it going to be our input or output, this value? Is that what we want to know? Yes, that's what we want to know. So that's going to be our dependent variable or output. Running out of space over there. And then D is going to be our independent variable or our input. Okay. I don't know if you can hear that in the background, but my wife is watching Cake Boss at the moment. So if you hear that in the background, enjoy. So our equation ends up being, remember, it's in the form y equals mx plus b. This is my rate of change. This is my initial value. So here, my rate of change is 200,000, and my initial value was 1 million. Boom. There's the equation of my line. Let's look at this second example here. To be a member of a gym, you must pay a one-time $25 entry fee. All right, one time. That leads us to know that it is, that's right, initial value. And then a $10 per, there is a kitty cat. That will be our rate of change. Okay, so we're talking about the whole cost. How much does it cost you to be a member of the gym. So the cost will be the dependent variable, and then how many months you're going to be a member will be the independent variable, and we end up with the equation C. I guess I keep circling the stuff here, but what I should be looking for is my highlighter. What happened to my highlighter? It used to be up at the top here. There, I guess it's called markup now. There we go. So C equals 10M plus 25. Notice the $25 fee is the initial value because it's what we pay initially, and 10 is the charge or the change over the months. So I hope that you're seeing a whole bunch of the exact same thing we've been doing here. We're just identifying the rate of change, the initial value, and plugging that into slope-intercept form to find our equations. Okay, so I'm going to help you in this next section where it says solving equations. Another thing that we may want to say, in addition to solving equations, is, I'm going to stay with red, is solving equations and evaluating equations. Remember, there's a difference between solving equations and evaluating. I think solving equations, we might solve for a variable, where evaluating is plugging in something that we know. That's the only difference between those two. So this first example right here is an example of evaluating. So we have some linear function right here. We know, again, it's linear because it's all to the first degree. And we're saying, hey, let's see what's happening. Consider a gym membership from above. So here's our equation, 10M plus 25. What happens if we were to be in that gym for 12 months? How much would that total cost be? Well, we just simply plug in the 12. And then 10 times 12 is 120. 120 plus 25 is 145. That's evaluating an equation. I don't think we have any problem with that. We've been doing that all year. Not a big deal. However, sometimes we want to solve for, well, I guess another type of evaluation is, instead of knowing how many months we are, let's say we're willing to spend up to $365 for this gym membership. How long could we possibly, be a member of this gym if we're willing to pay $365? So we put that in for the total cost, and then we solve the same way. Remember, this right here, we're subtracting 25 from one side. Whatever we do to one side, very good, we do to the other. And then 25 minus 25 cancels on one side, and then 365 minus 25 over here is 340, and then divided by 10. 340 divided by 10 is 34. You should be able to follow this step by step. And if you struggle with that still, you need to tell me. If you can't follow that chain of events and that mathematical computation in this problem, you need to tell me, okay? Because we need to work on your solving of equations. Later in this chapter, that's going to be our focus, is solving equations. So I'm going to stop there as far as the reading and highlighting goes, and I'm going to let you continue on. I think you got a good grasp of what we're doing here, and I'm going to now jump into the notes and do a few more of these problems or a few examples for you. Make sure that you finish reading and highlighting. You see there's a whole nother, 2 pages here of notes, maybe 2.5 pages of notes. And then, of course, you'll be doing your homework. Oh, let me hide that. You don't need to see that. So let's go to our notes and the things that I want to talk about today. So I want to give you a few examples, and I want to work through those with you, even though I can't hear what you're saying. All right, so we're going to create an equation solve. We're going to be given an example. In this 2.3a, we're going to be given situations, and we have to come up with the equations. Remember, we're dealing with y. Oops. Let's start by erasing that. Let's go here. Let's go y equals mx plus b. Those are the same 4 items we talked about yesterday. This is our output. This is our input. This is our rate of change. And this is our initial value. We need to identify as many of those as we can within each problem. All right, so example 1. You have $95 in your bank account. And you add $8 every week. Every week. That's kind of sounds like per, doesn't it? Rate of change. So if I had $95 in the bank to start, don't you think that would be? Yes, my initial value. Very good. So I know my rate of change. I know my initial value. How long will it take to have $375 in my bank account? Well, at $375, that's going to be my output, right? So we created an equation that looks like this. My output is $375 equals my rate of change is $8 per week. Plus I had $95 in the bank to start. Now, anytime that you have an equation that has only one variable, a lot of times we end up with y equals 3x plus 1 or something like that when we have two different variables. And there's a whole bunch of different possible solutions. But when you only have one variable, like we have right here, there's the only variable, that 8w. The w is the only variable. If that's the case, then we should be able to solve for that variable or isolate it. So we start by, what do we do first? Well, one thing I like to do is cover up that 8w with my finger. And I know you can't see me doing that, but I think cover up the 8w with my finger and I say, hey, what's with it? Well, plus 95. So I'm going to subtract 95 from here, and that cancels. But whatever I do to one side, that's right, I got to do to the other. So 375 minus 95 is 280 equals 8w. Now what? Yep, divide by 8. That's 8 times w, so the inverse of that or opposite is divide. 8 divided by 8 is 1 or cancels. And 280 divided by 8, you could use your calculator at this point, but 280 divided by 8 is what? 3 times 8 is 24, 40, 5 is 35. So W equals 35. So it'll take me 35 weeks of $8 a week allowance in order to have $375 in my bank account if I already have $95 in it. I hope that you were able to identify the rate of change, the initial value, and then, of course, your input and output rather easily in that example. Let's try another one. Example 2. You have $9,050 in your bank account. What do you think that is? $9,050. Anybody? Yep. It's your initial value. And you spend $25 each month. Each or per month, right? That's right. Rate of change for internet service. How much will you have in your bank account after 6 months of service? Now it's telling us how many months. Well, months would be my input, right? Or independent variable. So I'm going to have y equals 25m plus 9050, right? But now I know I got 6 months, right? So then I plug in that 6 for the months. So y equals 25 times 6 plus 9,050. Well, 6 times 25 is 150 plus 9,050. So y equals 9,200. I'll have $9,250 in my bank account if I... Whoa. No, I won't. It's not going to be plus 950. I'm spending it. Look at that. So I'm not going to have 9,200. I'm going to have 8,900. I almost missed the fact that we spend that much. And since we spend it, it has to be that's right, a negative. And my wife is finding something funny. Can you hear her laughing? All right. Next, there are 4 runners racing their bikes. Here's the information based of distance in meters based on a time. So distance is based. What does that tell us? It tells us that this is the dependent variable or the output, and that the time in seconds is the independent variable or the input. Okay. Let's look at these rates here. Joe goes 4 meters per second. So his distance is 4 meters per second. Catherine bikes 2.5 meters per second with a 120 meter head start. So Catherine, her distance is 2.5 meters per second, plus she had a 120 meter head start. Now, did you notice how easily I made that equation, or both of those equations? Let's look at Tamal. Tamal bikes at a rate based on this equation. D equals 3t plus 100. No problem. And then Prima bikes at the race based on this equation. What's she missing? Or he, whoever it is. What are they missing? That's right, they have no initial value, or their initial value is 0, but of course we wouldn't write plus 0. So now that we have 4 equations there, let's come up with some answers to these questions. Who bikes the fastest? In other words, who has the fastest rate of change, and how do you know? Well, 5 halves equals what? Well, 2 goes into 5 2 times with 1 left over, or 2.5 times. So this rate of change is 2.5. This one's 2.5, so those two are the same. This one is 3, and this one is 4. So who goes the fastest? Joe is most definitely fastest. Why? Because he has the largest rate of change. Who is the biggest head start, and how do you know? Well, Catherine had a 120 meter head start, and Tamal has a 100 meter head start. Joe has no head start, neither does Prima. Whoops, right there, Prima. So who has the biggest head start? Catherine. Now, I might want to say Catherine has the biggest head start. I might want to use the question in the answer. Who would go the furthest in 60 seconds? Now, in this case, I need to take that 60 and I need to plug it in all of these cases. Let me go to a red here. So my distance here would be 4 times 60. Well, 4 times 6 is 24, so that would be 240 meters. 2.5 times 60. 2 times 60 is 120. So 150 plus 120 would be 270. And then this 5 halves is the same as Catherine, but there's no head start, so that would be 150. And then over here, 3 times 60. 3 times 60 plus 100 would be 180, plus 100 would be 280. So 240, 270, 150, and 280. Who goes the farthest? Tamal. Tamal would go the furthest in 60 seconds. Who would win a race if the race were 2,000 meters long? Let me give those equations again. We got Joe is distance equals 4s. Catherine is distance equals 2.5 s plus 120. Tamal his distance equals 3s plus 100, and prima was distance equals 5 halves times s. Okay, and we want to know who would win if the race were 2,000 meters long. So in this case, 2,000 equals 4s divided by 4 divided by 4. 500, it would take 500 seconds for Joe. 2,000 equals 2.5 s plus 120. First thing I would do is subtract 120 from both sides. So that would be what? 1880 is 2.5 s divided by 2.5 divided by 2.5. How many people look at that and think to themselves, I can't do that? Well, guess what time it is? That's right. You can pull out your handy-dandy calculator or Desmos and go ahead and do that. 1880 divided by 2.5 and see that it is 752 seconds. 752 seconds. The next one, 2,000 equals 3s plus 100. We'll start by subtracting 100 from both sides. So 1900 equals 3s divided by 3. I know I'm going really fast here, but I'm on video and you can always pause it and look at it, or pause it and do some calculations yourself if you need to. But 1900 divided by 3 is 633.3 equals s. And the last one is 2,000 equals 5 halves s. Now, this is as a fraction. I know you guys don't necessarily like fractions, but to get rid of a fraction, I can divide by 5 halves or actually multiply by 2/5. And that cancels, and all I'm left with over there is s. Well, 2,000 times 2/5 is 4,000 over 5, because that was really 2,000 over 1, right? We multiply straight across. 2 times 2,000 is 4,000. 5 times 1 is 5. 4,000 divided by 5 is 800. So the question is, who would win if the race was 2,000 meters long? So we got 800. That would be fourth place. We got Catherine at 752 seconds. That would be third place. Tamal, 633 seconds. And Joe, most definitely, would win a race of 2,000 meters long. So there you have it. There are your notes from section 2.3. I hope that you read and highlighted that. Just as a reminder, your homework is 2.3a, even problems. Good luck. I hope that y'all have a great day.